Thank you all for being here. Thank you, Martin, for delivering this lecture today. Go ahead.
Okay, thank you, Robert. You can hear me and see my slides, I guess. Right, then I can start. So the title of the talk today is Metrology and Material Characterization of Microelectromechanical Systems, MEMS with high-frequency ultrasound, more specifically laser ultrasound. And the motivation for that actually comes from industry. And as you probably know, wireless telecommunication is based on transmission of radio signals at gigahertz frequencies. And for example, in every mobile phone, one of the first components is a bandpass filter. And this filter is usually composed of electroacoustic resonators, for example, as shown here, Bohr resonator, bulk acoustic wave resonator, which is a classical MEMS device. It's based on, it's a multi-layer system, actually. You can see a sketch here, but I think the basic idea is quite easy to understand. It's a piezo layer and the top and bottom electrode. And the electrical voltage is applied here and it's converted to the acoustic domain and back to the electrical domain. And due to a resonance condition, the electrical signals can be filtered very efficiently by combining several such Bohr resonators. And yeah, the question is, or the need from filter producers is to get information about the single materials which are used to construct such a device, which can be piezoelectric materials, metallic materials, and also dielectric. And the basic interest is to be able to characterize the acoustic loss, because you also might know that usually losses strongly rise with frequencies, and frequency with acoustic frequency, and that at gigahertz frequencies losses are high, which means reduction of battery lifetime and decrease of performance. So the task is to characterize the losses at gigahertz frequencies by using laser ultrasound. And this will be one example I will give in my talk. And the second one is to characterize this whole MEMS device, this resonator. And of interest are here, for example, thickness changes or defects, thickness variations. And yeah, that will be the second application example of laser ultrasound. And for that, we need high frequency laser ultrasound, because these devices operate at these frequencies. I'd like to start with a very brief introduction to laser ultrasound. So here you can see the most basic laser ultrasound experiment. You have some kind of sample, can be metallic, for example, and a pulsed excitation laser, usually nanosecond pulses, high pulse energy. And this laser, for example, hits this specimen here. It's absorbed at the, if it's a metal, it's absorbed at the boundary. Due to the absorption, there is production of heat and expansion of the sample surface. And due to this rapid volume expansion, the sample itself acts as a source for ultrasonic waves, which then propagate through the specimen and are probably back reflected and bouncing back and forth, for example. And you can, for example, detect these waves at this side of the specimen, again with a laser vibrometer. And if you look at the time trace in an oscilloscope, you can see several echoes typically from the back and forth going signals here. And for example, you can use the time delay between these echoes to get information about the speed of sound, which is related to material properties. Also, you can compare the amplitudes of succeeding echoes, which gives information about the acoustic damping. So this is a basic experiment, and it's usually, this technique is is suitable for bulk waves, for frequencies, acoustic frequencies up to, let's say, 100 megahertz roughly. If you use surface acoustic waves, then maybe a little higher, but it's hard to achieve gigahertz frequency range. There is another technique which we call frequency domain laser ultrasound, which is used to achieve gigahertz ultrasonic signals. I will show that later. Here is the basic operating principle. This time the excitation laser is not pulsed, but it's modulated. The amplitude is modulated at a certain frequency. And so the sample is kind of forced to vibrate with this frequency of this laser oscillation. And again, a vibrometer, laser vibrometer can be used for detection. And this time, we don't use a oscilloscope, but the lock-in amp. So we use phase-sensitive detection. We get the phase and the amplitude of the signal. And there is the advantage of this technique is that you don't need, compared to the first technique, the time domain laser ultrasound, that you don't need that high laser powers, because you just excited a specific single frequency, so the excitation power can be decreased, which is very interesting or useful for thin, fragile specimens, typically used in semiconductor industry, thin layers, because if you shoot at them with a high power laser, you simply will destroy them. But with this technique, due to the high sensitivity of this phase sensitive detection, you can use low powers and stay in the non-destructive regime. I will show you later how we can achieve gigahertz frequencies with this setup. But before that, I will give a short introduction about the kind of waves we are using. And for material characterization and device characterization, typically these are so-called lamp waves. And if you look at this sample, this is a plate, and this plate acts as a waveguide for acoustic waves. So as indicated by this arrow here, like in an optical fiber, for example, also here for the acoustic waves, the waves are confined by the boundaries and they propagate within the plate. And you can characterize the behavior of these waves, these lamp waves, by, for example, calculating the dispersion curves, which is shown here. If here on the x-axis the acoustic frequency, and on the k-axis is the wave propagation number, the wave number, which is the inverse, proportional to the inverse of the wavelength. And each line here or each point here is a allowed wave mode. And we typically use plate resonances for material characterization, and plate resonances appear here at vertical tangents when the group velocity vanishes in this dispersion curve. This is the definition. And if the group velocity vanishes, like this point, for example, then a wave package won't travel away from its excitation source. And so the energy is kind of confined locally, which is very counterintuitive, I would say, because it's still waves. And there are two types of these resonances. The ones with zero finite wave number and wavelengths are called zero group velocity waves. They oscillate like this. This is just an example of one specific mode. And another type is called thickness resonances. You can see here they have zero wave number. That means infinite wavelength, which means also that the plate surfaces, they vibrate in phase. So this is typically the mode which is used in these Ball resonators. Yeah, and it is very well known that this type of resonances can be measured very, very well with laser ultrasound, at least in the megahertz frequency regime. So if you have a steel plate, for example, with 1 millimeter, use a pulsed excitation laser, record the signal at the opposite phase with an oscilloscope here, you do a Fourier transform, then you will get such acoustic spectrum and with very pronounced peaks. And these peaks correspond to these zero group velocity points or points of vanishing group velocity. Okay, and these resonances have a very interesting or useful property, that is that they scale inversely with the plate thickness. So if you want to go for higher frequencies, for example, you can, for example, produce a thinner plate, and then the whole spectrum will shift up to higher frequencies. How can we use these resonances, or what information is contained in them? First of all, the center frequencies, they are related to the elastic properties of the plate. If it's an isotropic material, they are given by the Young's modulus and the Poisson's number, and also by the plate thickness. So for example, if the thickness is known and one measures two resonances, one can extract information about the elastic properties, and vice versa. If these are known, one can get information about the thickness of the plate. But what we will use is not the center frequency position in the first example I will show, but the peak width. And this peak width is related to the acoustic loss and the temporal decay rate. And the higher the acoustic loss is, the broader the peaks will get. So this can be used to get information about the loss in the material. This brings me to the first example. The application example is the measurement of acoustic loss at gigahertz frequencies. And as I said, there is this universal scaling behavior. And if you do the calculations, if you want to go, for example, from megahertz frequencies, as from the steel plate, the example shown before, to gigahertz, one has to reduce the plate dimension or the plate thickness from millimeters down to micrometer range. And we investigated electrode materials of these Bohr resonators, tungsten and aluminum. And we had to produce thin plates, freestanding plates, which can be done by standard photolithography techniques. Here's a sketch, and here is a microscope image of such a plate. So this here is a freestanding, free vibrating plate of tungsten with a thickness of 1.6 microns. How can we measure at these high frequencies? So this is again the frequency domain laser ultrasonic setup. And in the past several years, we kind of extended it and optimized it for operation at gigahertz frequencies. And I don't want to go into details here. What we're using is a diode, electro-absorption modulable diode, which is subsequently amplified by an EDFA. This is just focused. This is fiber-based and focused into a sample. And as explained before, the laser is amplitude modulated and forces a vibration at a certain frequency f. This is the excitation branch. And the detection is done by a stabilized Michelson interferometer shown in green light path here. And we record in a phase-sensitive manner by using a vector network analyzer similar to a log-in. And by that, we can get the out-of-plane displacement, the vibration, the amplitude, and the phase. And for example, if you have a look at a tungsten plate with 1.8 microns in thickness, here is the acoustic spectrum. You have the acoustic frequency and the magnitude of this out-of-plane displacement. You can see again very distinct resonance peaks up to, let's say 4.2 something gigahertz. And again, these resonances can be very well assigned to calculated points of vanishing group velocity, as explained before. Okay, how can we get the attenuation or the loss out of such measurements? Therefore, we developed two approaches. The first one is based on this first type of resonances, the zero group velocity resonances, which are basically some kind of combination of longitudinal and transverse wave motions. And yeah, you can see here two peaks, first CGV peak and second CGV peak of a tungsten plate, 1.8 microns in thickness. And because there is coupled motion, wave motion, to get information about both damping channels. Okay, first you can extract this decay rate by some data fitting, for example, from this resonance. And because it's coupled here of longitudinal and transverse wave motion, we need another resonance. So we want to extract longitudinal and transverse attenuation coefficient, denominated as alpha L and alpha T here. And to get that, we need more information. And what we did is we produced a second plate, which is thinner, shown in red here. So it's 1.1 micron. And due to this scaling behavior, the CGV1 resonance, which was in the thicker plate here at this frequency, in the thinner plate, this shifts upwards to higher frequencies. And actually the goal was that we get it at the exactly same frequencies. We didn't kind of get that done because we didn't know the material properties so exactly, but it's close enough. And from that, we can also, again, extract the decay rate of this second resonance. And if you assume it's approximately at the same frequency, you can apply a model where you can calculate the bulk wave attenuation coefficient from these two measured values. And yeah, this can be done. And yeah, you get at one frequency from measurements of two plates, both attenuation coefficients, which is, I think, not usual, because the usual way is to calculate or to measure just the longitudinal acoustic loss from bulk echo experiments. So here you can get both damping channels, which is kind of nice. But you can also use thickness stretch resonances. It's an example in aluminum. And these have a different mode shape, a different mode of vibration. And they are directly related to longitudinal wave motion. And you can see here, there's this blue trace. You have these resonances in aluminum. There's the CGV resonance. And in contrast to the red, to the tungsten plate, you can see here also this L1 resonance, this longitudinal resonance, which we couldn't see here. It's just too tiny. So we couldn't measure it in tungsten, but in aluminum, due to different thermal properties, it's getting excited. So we can use that one. And again, from some kind of data fitting, the peak width, the peak shape, you can extract the decay rate here. And this time, this is directly related to the attenuation, to the longitudinal attenuation coefficients with the longitudinal speed of sound, which is known. So this is a more direct way of measuring attenuation, longitudinal attenuation. And again, we use this scaling behavior of the resonances, and we produced different plates. So this is has a certain thickness, but you can produce a series of plates, and then the resonance frequency is shifted. And finally, you obtain, as a function of frequency, if you repeat that process, you obtain the progression of the attenuation, of the longitudinal attenuation for aluminum here. And this was kind of nice because we could fit a power law. And yeah, here's just a comparison of two values for tungsten. Okay, so this was the first example of characterizing acoustic loss at high frequencies. Of course, we can also get information about from the center frequencies. We can get information of the elastic properties, but this has been done before. So this was kind of a novelty, and it's published here in this paper. This brings me to the second example, which is about imaging very tiny thickness changes in whole Bohr resonator stacks. And this was kind of a demonstration experiment, and to demonstrate what the method is capable of. And what we did is we used a Bohr resonator, which is shown here. As I said in the introduction, it's a multi-layer system. It's an acoustic Bragg mirror and a piezo covered by bottom and top electrode. And there is also a passivation layer, silicon nitride on top. And we imprinted, or we etched this. So this is the top view, an artificial checkerboard pattern with a side length of 30 microns into the top layer. And the height change here, we had 3 different samples. This was 1 nanometer or 4 nanometer or 8 nanometer. And we wanted to see if we can resolve that thickness change by using this plate resonance technique in combination with the frequency domain laser ultrasound. And here you can see a point measurement. So this is a microscope view, a top view of this resonator. Here is the detection laser. And again, you can see here, there is an acoustic spectrum. And this, although it's a multi-layer system, due to this Bragg mirror, it also behaves kind of like a plate. And due to that, you will also get these sharp resonances. Here is, again, this zero group velocity resonance at 1.7 gigahertz. And yeah, you can do some calculation. Everything agrees with theory. And to do some imaging, we just did a narrowband scan of the acoustic frequency around this expected peak here, because we know where it is now. This is just one point, and we scanned across the area of this resonator. So here are actually these checkerboards. You cannot see them. They are so tiny in height change, you cannot see them in the microscope. And here is the result. And this is, I think, very impressive. We just used the position, so the frequency, as a contrast mechanism, right? The frequency extracted from maximum here. Forget that. And if you just plot this frequency, the center frequency, as a function of the spatial coordinates, you can see that you very well resemble this checkerboard pattern. And it's very clear for step heights of 8 nanometer, still for 4 nanometer, and we could even see 1 nanometer thickness change. So this means this technique is very, very, very sensitive to local thickness changes. And by using this known formula, you can directly translate this frequency into a thickness change. And here, for example, this 8 nanometer, this was the nominal thickness, which was etched, so this agreed very well. Also, we are curious how good our method is compared to standard methods for mapping thickness changes in nanometer range, which would be an atomic force microscope. And you can see here a tiny bit of this sample recorded by AFM, and it very well agrees with the AFM measurement. Yeah, maybe one remark. So this method, this was just a demonstration. So this is rather artificial, you know, it's not a real world problem. We just wanted to do a benchmark. And the method is very sensitive to local thickness changes. So this is maybe the takeaway message, and not only to local thickness changes, but to also to changes in the material properties, if there are any. So if the elastic properties would change, or if there would be any defects, you would also see that probably. Okay, this brings me already to the end of my talk. I hope I was able to convince you that plate resonance is measured with this frequency domain. Laser ultrasound system can be very well used for characterizing thin single layers, or also multi-layer systems in a non-destructive way at gigahertz frequencies. And therefore, I've shown two kind of examples. One was about investigating single layers or plates to retrieve the acoustic loss at gigahertz frequencies. We developed two different methodologies and applied them to tungsten and aluminum. And the second example was the imaging of whole resonators, of whole stacks, of whole MEMS devices with this technique. And we were able to detect thickness changes down to 1 nanometer. And this is in terms of the Z resolution comparable to AFM measurement. And it has the benefits of you don't need to put the sample in a chamber, and you don't have contact to the sample. All right. Last but not least, I would like to thank Robert for organizing this session, and of course you, the audience, for your time and for listening. Thanks.
Thank you for the excellent talk, Martin. Thanks a lot.